Let's begin. Okay, welcome again. Exciting times. Today we are going to do our first partial differential equation by adding time to this problem. We did this problem last time. It was steady state heat transfer problem in 1D, and I needed that because I wanted to show you where a linear solver will show up to solve the system of equations. We will do this again in 2 dimensions. In that case, in 2 dimensions is going to cross off the Poisson equation, right? This is the Poisson equation in 1D. We need to do this in 2D. So, that was the purpose of this. But not only that, now we're going to augment this by adding a time evolution dimension to this problem. So this problem, if you think about it as if you think of it as the steady state process of a evolutionary or time-dependent PDE, all you have to do is add a time derivative to this to make it time-dependent. And what I will do, so if you notice, if I take this to the left-hand side, so they become second diffusion minus some source, right? And then you add a time derivative to the left-hand side, that gives you an unsteady diffusion equation. There's no convection. There's diffusion term on the right-hand side, and there's some source term on the right-hand side. So when it's at steady state, this becomes 0, then you recover that other problem. But now this process allows us to see the evolution of that other problem, but over time, okay? And it's a good toy model to start getting towards the unsteady advection diffusion equation, which is the model for Navier-Stokes. And in general, I will write this in this form. I'm going to step away from T, temperature. I'm going to use U, again, to enforce the idea we're going to be solving velocities, for velocities. du by dt equals some diffusion coefficient times second derivative of U, which is the diffusion term. So this is the diffusive, the net diffusive flux into the control volume plus some source term, okay? Now, when we add time, okay, we need a time integrator that's what we call them colloquially, to solve the time evolution of a differential equation. We already saw how we discretize in space. We will now learn how we discretize in time and combine them together, okay? So just like finite difference approximations, the time derivative can be approximated in time. So what I will show here is a portion of a grid in space at point I. I'm showing the 2 neighboring points because that's the widest stencil that we used last time for diffusion. I plus minus 2i plus I minus 1, right? That was the widest stencil we used. We never used I plus 2 or I plus 3. So I'm just going to show these 3 points here. And I'm starting at some initial condition, t equal t0, usually 0. And I'm going to index this in time with a superscript n. This is not a power, okay? It's just a superscript. Just like this is a subscript, I'm going to put the superscript for time up here, okay? Or the counter for time up here. Because in time, we're going to also have a grid, just like we have in space, I minus 1, I plus 1. We're going to have a grid in time as well, n plus 1, n plus 2, and so on, okay? So our purpose when we do a partial differential equation is we want to evolve each one of those points in time at some time interval, delta t. So we're going to go from t0, our initial time, a single time step, which defines the time step size or the spacing in time. So now you have the spacing in space, and you have the spacing in time. So if you think about it this way, as that adds that extra dimension in time, okay? So our purpose would be to evolve each one of those points in space, evolve them also in time, right? Now, if you follow my indexing nomenclature, these become at time level 1. So I'm going to put 1 in the superscript, okay? The subscripts always refer to spatial indexing, okay, on the grid. And then you continue this process until an arbitrary time level, n plus 1, and so on. So just like we chose I plus 1, I minus 1, we're going to choose n plus 1, and n minus 1 as our representative the representative points in time, right? So in space, we chose point I to be an arbitrary point in space, I plus 1, I minus 1. In time, we're going to choose n as our representative time level, okay? And that relates to things at n minus 1 and n plus 1, okay? Now, there are two ways of handling, in general, of handling the time evolution of a differential equation. You could try to approximate that slope, the time derivative, at time level n, okay, where the right-hand side, everything on the right-hand side is evaluated at time level n. Okay, so you use that to advance in time to n plus 1. That gives you, so that would be using a forward difference. We will call that explicit in a second. Or you could use what is a backward difference in time, and instead of evaluating the equation at time level n, you evaluate it at n plus 1. And then everything becomes at n plus 1. Now, these forward and backward differences for the time derivative, they look the same, right? Because this is at, remember here, at n plus 1. The backward difference is un plus 1 minus un over delta t. This is the forward difference, but at time level n. So it's still un plus 1 minus un over delta t. But what matters here is the right-hand side. Where is the right-hand side evaluated? In the forward difference, the right-hand side is evaluated at n. In the backward difference, the right-hand side is evaluated at n plus 1. I'm giving here the two simplest ways to untangle that time derivative. There are more complicated ways of doing that. We'll talk about that later. Let's learn first how to walk. Okay? Now, this creates two categories of integrators in time, which you didn't see when we did it in space. In space, all the points were kind of connected to each other. So by definition, in fact, a steady state problem is always an implicit problem. There's no explicit integration in space. You're always implicit. You have a system of equations. You need to solve them all together. But with time, the story is different. If you choose to go with a forward difference approximation, you have information at time level n, and you're after information at time level n plus 1. Then when you look at this equation, well, I have everything at n, everything at n. It's a simple algebraic evaluation to evaluate things at n plus 1. Right? So we call this explicit time integration, where the right-hand side is evaluated in terms of the past. So new information, we're always starting at time level n. We know information at time level n. Why? Because you're starting from t equals 0, where you know the initial condition. Right? So you're always starting from somewhere that you have information. To move to n plus 1, all you need is information that you know. And that is called explicit time integration. And that forward difference that I mentioned in the previous slide is actually called the forward Euler method, where the time derivative is evaluated at time level n with a forward difference approximation. The right-hand side is also therefore evaluated at time level n. And that automatically defines this explicit integration where you immediately can compute un plus 1 in terms of things that you know. And then this becomes your formula. U at point I in space at time level n plus 1 is equal to u at point I in space at time level n, so that's the past, plus this distance in time, which is we call the time step size, delta t, times everything on the right-hand side. What is the right-hand side? Advection, diffusion, and sources, right? Everything at time level n. Now, this is cool because you have information at n. So these are just numbers, right? And then you can immediately compute things at n plus 1. So the strategy would be we're going to visit every point in space and move it forward. We can visit all of them and move them forward together, but they're not dependent on each other. These points here, they don't depend on each other. They only depend on things that are known. These points, this one depends on all of these points. This one depends on all of these points. But these two, they don't depend on each other. So you can either visit each point and move it in time or move them all together. So we're going to do the former. We're going to visit each point. Or actually, we're going to do array slicing, move everything together in one shot. Okay, all of those points here. So we're going to take all of these points here and move them all in one shot, okay, using this formula. Very easy, very simple. Explicit time integration. In a nutshell, explicit integrators result in an algebraic relation, that can be evaluated promptly. There's no nonlinear solvers or systems of equations, none of that. Okay? They're very simple, lightweight, and easy. Okay? Now, on the other hand, now explicit integrators have issues, etc. We will learn about all of that, I promise you. Okay? But I want to get you to do CFD first, and then we revisit the issues. Implicit time integrators, on the other hand, they evaluate the right-hand side in terms of the future and the past. So in general, in an implicit time integrator, you're evaluating you evaluate the entire equation at n plus 1, okay? So du by dt equal right-hand side at n plus 1. That's it. You're taking the entire PDE and saying, I'm going to evaluate it in the future. And then you approximate the first derivative in the future using info from the past, but the right-hand side, it's still in the future. So what you're saying is, I need to evaluate this point, I need to know what's happening here at these points in the future. And to evaluate this point, I need to know what's happening here. So they become all coupled to each other. Okay? That's why they're implicit. They're implicitly dependent on each other. And in general, that will result in a nonlinear system of equations. Because in general, this right-hand side could have nonlinear advection terms, which we will see with Navier-Stokes. If the right-hand side is linear, it will still be implicit, but you will have to solve all of those points as a system of equations concurrently, not advancing them independently. They have to be solved just like we did the heat transfer problem for the rod. We couldn't do a single equation at a time. We had to put them all in a system of equations and solve them together. So that's implicit, okay? Same thing will happen here, except it will be a nonlinear system of equations in general, okay? So that's implicit time integration. Now, implicit integrators are superior in some sense to explicit integrators because they allow you to be generally stable. Okay, we will get to that point later on in the course. But they are less kind of intuitive, and you have to deal with nonlinearity. In big codes, in big CFD problems, this could be an issue because a nonlinear solver, you cannot always guarantee that it's going to converge. It's very costly. The development, writing the code for it is very complicated. Okay? Whereas with the forward Euler method or explicit integrators, it's kind of easy. You just move every point in one time step, and you're done. Okay? The problem with the explicit integrators, as we will see next, is that they can be unstable. Okay? All right. So let's go ahead and start with our first example, or second example, first example today, second example in this series. And it's one-dimensional unsteady diffusion with FTCS scheme. Okay? S is not for sad, okay? FTCS scheme. S, let's see what S means. Okay. So I'm going to take this equation. It's an unsteady diffusion. There's no source term. We will add the source term and the code together. Okay, so now I'm turning into partial derivatives, diffusion coefficient, positive number. And now we will start with an initial condition that only depends on space, right? That's an initial condition, only depends. So you can do a sine or a Gaussian function. And I'm going to anchor the values at the endpoints to 0 for simplicity. Doesn't matter. You can play with those numbers in your code. That's fine. And we will use forward in time and central in space approximation. Now look at this beautiful animation. Okay? That's the FTCS scheme. Okay? So forward in time, central in space. You will often find things like that. You might find BT, BS, backward in time, backward in space approximation, or FTBS, or FT, we'll cover some of those. So that's an easy way to communicate things when we're working on the course. So I know now with an FTCS, so if you go and Google now, FTCS diffusion equation, you'll immediately get results about this equation using forward in time, central in space approximation. So what we will do here, the forward in time automatically defines that this is going to be evaluated with a forward Euler method, so it will be explicit. And central in space, we will be using a central scheme on this diffusion term. Okay? So let's see how this works. We'll evaluate the derivatives at time n. So we're going to take this entire equation at some point I in space and some point n in time. And we're going to do forward approximation on the derivative. So you get This is the forward approximation for the time derivative, and this is the central approximation for the space derivative. Mind the indexing. Okay? Everything here is at level n. This is the past. This is known. Okay? So I like to put these diagrams reminiscent of what I showed you earlier. This is saying that point I n plus 1 only depends on the information at I minus 1, I, and I plus 1 at time level n. Okay? Only these 3 points are contributing to information at that point. And then our simple algebraic formula is simply this. This is what we're going to program. We're going to start with an array of points and then move through each point. Okay, so that gives us level n. Move through each point and apply this formula. Couldn't be any simpler than that. We're going to do it very nicely in Python. Okay? So we're going to Pythonify this, and we will experiment with different initial conditions together. We're going to look at sinusoidal initial conditions. And I will also show you a really cool thing about diffusion. We're going to take that sinusoidal signal, and we're going to change the frequency and look how diffusion acts on different frequencies. And you'll recognize why diffusion is a very good smoother of noise. And that is going to have implications once we get to advection a little bit later. Okay? So, and then the question, is diffusion more effective on high or low frequency signals? And we will try with different time step sizes as well. We're going to change delta t. Okay? Now, before that, I want to talk a little bit about Python array slicing. Does anybody not know what array slicing is? Okay? That's fine. Okay. All right. So a NumPy array is just a sequence of numbers that are located in memory like this. I came up with those numbers, 5.4, whatever. Okay? And you can do forward indexing like we talked about last time. You could go, you know, if this array A, so A0 is 5.4, A1 is 7.2, and so on, right? So A0 is 5.4, A3 is 21.2. Or you can do a reverse indexing. You start from the end. This is index -1, -2, and so on, right? So A minus 1 is 0.3, and A minus 5 is 33. So you go -1, -2, -3, -4, -5, right? We talked about that last time, so good. But you can also get subsets or views of an array. And this is done, this procedure is called slicing through an array. So there are reasons sometimes where I want to take this subset and that subset. So if you want to think about it with me for a minute, when I'm doing ui plus 1 minus ui minus 1, so that if it means this point minus that point, and this point, or this point minus this point, this point minus this point, then I can take two arrays and subtract them from each other in one shot, right? So that's the benefit of slicing. All right, let's see what slicing looks like. It has this format. If you type the name of the array A, you put those square brackets, and you give it two numbers separated by a semicolon. Okay, this will return, so starting from a starting index to a stopping index, this returns a view, not another array, just returns a window, like it shows you what it is. It's not a new array, it's not a copy of the array, it's still the same array, but just a view of it, okay, of the array that contains the elements a start plus 1, etc., all the way, not to a stop, but to a stop minus 1. So think of this as an open interval, okay? So the last entry in this view is not stop, it's at stop minus 1. I'll give you an example. So for example, A02 is going to return A0 and A1, okay? So it will return 5.4 and 7.2, okay? Now, note that this is not a copy of the array, it's a view of it. So if you modify the view, it's going to modify the original array. Okay, be careful about that, all right? And that's nice because you don't want to, every time you make a view, you create new memory, it's going to mess up, it's going to fill up your code, okay? If you want to make a copy, you need to be explicit about that. You can also go all the way to the end. So if you type A3 and semicolon without a stop, it's going to give you everything from index 3, so it's 21.2, all the way to the end. So it will give you 21, this guy, this guy, this guy, and that guy, right? You can also index in reverse. So A3 minus 1, Okay, it's going to be, what is it? A3 minus 1 is going to be 21.2, 7.8, and 10.1. Now, because the minus 1 is not included, okay? This is different than A at minus 1. Remember, the stop, we always go back to this guy minus 1, right? So here's kind of a summary of those. There will be in the slides for you to look at later. All right, let's get our Jupyter notebooks and get coding. Yes?
Is that indexing work left to the left also, or just only to
Yep.
the right?
No, however you like.
So
Yeah.
A3
You could do A from -5 to -2. Right. Yeah. But it's all, no, yeah, it needs to be, it's always in the sequence. I get your question. So yes, it's always going to give you, it's not going to change the order of the array. It's always going to go from the left of the array to the right, okay? Yeah, good point. Okay. All right, so let's get a new Jupyter notebook up and running. All right, going to create a new notebook. Now remember the boilerplate I mentioned to you last time? Go ahead and grab that and just paste it in the first cell of your notebook, and I will call this in class 1D unsteady diffusion with FTCS scheme. Forward in time, central in space scheme, okay? For my boilerplate, let me copy it from what I did last time. We had import numpy as NP, right? Okay. I will need a few more things for the boilerplate. We will add them as we build the notebook together. All right. So first, I'm going to define the number of points in space. So define. First, let me add some. Solve the 1D unsteady diffusion equation with the FTCS scheme. Okay. We solve an equation and by partial t is equal to mu frac partial u by partial second derivative u by partial x squared. Okay, subject to initial conditions, subject to, we can do u of x t equals 0 equals some initial condition of x, and boundary conditions u at x equals 0 at any time equals 0 point equal to u at x at the end of the rod. So this is a 1D domain, right? Okay, this looks nice and neat this way. And we can, I'm not going to type a lot here because I want to focus on the coding. But in your notebooks, if I'm asking you for any reports in the homework, make it high quality. Write down, explain what you're doing. It will benefit future you as well when you come back to these notebooks. To me, I've done this 1,000 times. It's in my mind, and I have one notebook that contains all the info, so it doesn't matter too much to me. Okay. Define number of grid points in space. Okay, so you will notice that we always define the grid resolution in space. We don't really define the grid resolution in time. We only specify a time step size, and we say integrate from 0 to 10 seconds or 20 seconds, right? So you don't define an array in time. Rather, we're going to build that solution in time, one line at a time. Okay, we're going to start from t equals 0, go to t1, and save that, then go to T2 and save that, and so on. Okay? All right, so let's put n equal 101 Dalmatians, and L, again, 1.0, so length of domain. And I like to define the spatial coordinates because I use plotting. Zero, right? So we have some tricks up our sleeves now, all right? Okay, so let's now define our initial condition. Okay. I'm going to declare U0 as my initial condition. So let's call it capital U0. What do you want it to be? Sine, let's take a sine function. And p.sine pi x, okay, and p.pi times x. Okay. If you're in doubt, plot it. Okay, so let's plot it. plt.plot. I want to plot u0 versus x. Okay. And I'm going to add a grid, plt.grid. All right. Okay, maybe 2 pi x. 2 pi x. Just get it to look nice this way. Okay. Now, for those who took numerical methods with me, what annoys me about this plot? Look at that. It looks like crap, right? It's like this vector, not this like raster graphics. It's all pixelated. Look at that. If I see, like to me, if I'm reading a paper and somebody puts a plot like this, that's like grounds for rejection. It's not acceptable in this day and age to produce graphics that look like this. Whereas look at this, right? This looks so pretty and nice because these are vector graphics here, whereas this is turned into a raster. Okay, so there's a little trick in Matplotlib that allows you to produce nice, high-quality images in the notebook. Now, you can export this. When you export this figure, you don't export it as JPEG. Export it as PDF. Because PDF is a vector-type format. It's going to give you nice, beautiful graphics, okay? But to see those graphics here and not be annoyed, well, me, do the following. Matplotlib inline, and also config inline. Don't ask me how I got those. I didn't invent them. I found them somewhere on Reddit or Stack Overflow. So what this is saying is telling, look, Matplotlib, make all your graphics SVG. What is SVG? Scalable vector graphics. This is the quality that you get from a font. That's why when you zoom in, a font always redraws itself. Look at that. You can zoom into infinity. It will always redraw itself because it's a scalable graphic. And the way it is redrawing itself literally. Okay? So when you do this, notice what happens here. And it's not a trick with DPI. It's actually the plots are being redrawn. Okay? So see the difference? It's nice and clean. Right? So, okay, good. So now add that to your boilerplate. Okay? Now, another thing that discrete data, do not connect your data with lines. Or if you insist on connecting your data with lines, make sure you add markers. Discrete data is best represented with markers because it is discrete. It is not continuous. So I really, when somebody plots a plot like this for me with discrete data, I was like, where are the markers? So instead, just do it as a marker. So you could do a little symbol over here. Okay, you can change the marker size. Say marker size equal 3, and it makes it nice and slim. You can add a line to it. That's fine. Okay, because at least you know here that they are connected this way. But adding a line in a plot gives the assumption that these points are connected directly with a straight line. What if they're not? What if there's a wiggling in between any 2 points? You don't know that. Well, here we know, right? So, okay, we get that. But I like to do this because it also gives me an idea of how many points I have, right? So if I have 20 points over here, oh yeah, I can tell that this is pretty sparse, okay? So, okay. Are we in sync? Okay, let's do it. All right, now, all right. So I'm going to just step here and see what happens. Okay, that is going to be, if you ask a CFD practitioner one question, like what is your worst fear when you're doing a CFD? They're like choosing my time step size, especially if you're using explicit methods. Because you don't know if your solution is going to blow up. Okay, you run your calculation overnight, you go home and you come back the next day and they're junk, right? You've wasted an entire day's worth of work. Okay, so we're going to pick a time step size. I don't know. I'm just going to put 0. And just take this to, let's say, 10 seconds. Again, I'm coming up with these numbers. Okay, we'll see what happens, and then we'll play with that a little bit. Usually in a physical situation, you have guidance, what you're trying to do, okay? You know these properties that you need to do. We'll talk about time step size later, okay? And my diffusion coefficient, so check it out. I typed \m, press tab, and it turns it into a Greek symbol. If that works on your laptop, great. If it doesn't, just type mu for mu, okay? Mu, I'm going to do 1 e to the minus 2. So that's the diffusivity. It's in meters squared per second. Thermal diffusivity or diffusivity meters squared per second. Okay. And all right, now we're ready to actually do the integration. I'm not going to create an array to store things in time. Instead, I'm going to solve everything in one shot and store it in like a container so I can view the data over time. Obviously, I want to animate this. I want to see this sinusoidal pulse just kind of decay over time, right? Because that's what diffusion is trying to do. And what I want to do is I don't want to create a two-dimensional array, one in space and one in time. You might be tempted to do that. That's not a good idea. Instead, only focus on space. Your arrays need to be only in space. You solve in time one shot at a time, and you store that in a container. There's no two-dimensional arrays are very annoyingly complicated. You will see when we get to do 2D Navier-Stokes. So why add more complexity in time? This is 1D in space. Keep it 1D in space. We'll store time in a container. So what I will do, I'll create a simple container using this bracket. This is a container that will contain the solution in time. Okay, what does this bracket do? Python is really cool. If you declare a variable with open bracket, you can put monkeys in it. You can put whatever you want in it, in this container, okay? You can add things to it. And you can append arrays. You can say a.append, array 1, right? Array 1, or array 2, array 3, and so on. So that's what we will do, okay? So initially, our solution is going to contain, thank you for laughing at my choices. +1. Solution.append, our initial solution is going to be the initial condition, right? So we're going to solve with the initial condition. So we're going to add u0 over here, okay? And I'm going to seed my time at 0.0. That's my initial time. That's t0, okay? Or we're starting from t equals 0, okay? Okay, we're ready now to integrate in time. We are ready to advance in time, which is a better word, to advance in time. You can do this in many ways. I'm going to do it one way. I think it's simple and easy. I'm just going to do a while loop. While time is less than t end, do something. Okay? So while t is less than t end, do something. Okay, so do something. Okay, so what do I need to do? We need to solve that equation. Let's get our formula right next to us. So I'm going to move this to Creston. Okay, so we need to compute this formula. We need to say that the new solution is equal to the old solution plus mu delta t over delta x squared times old solution I minus 1 minus 2 old solution at I plus old solution at I plus 1 and so on. Okay? So first, I need my old solution. Okay? How do I get to the most recent solution from sol? So what if I do un is equal sol minus 1, right? That gives me the most recent solution, right? That gives me un. Sol could contain 1,000 entries, 1,000 arrays in it, right? Sol minus 1 is always the most recent. It's always at n. Okay, so that's un. Now I'm going to create, let's say, okay, grab the solution at time level n. Seriously, once we finish with this code here, subsequent codes are going to be very easy. Okay. Okay. So now that we grab the solution at time level n, sorry, not time level 1, time level n, we're going to create an array, or a new array, for the solution at n plus 1. And I call that np1. Okay? Why np1? This comes from years of wisdom developing like codes in big codes. And apparently, people use this nomenclature, un, unp1 for n plus 1, right? And so I've taken that, and I like it. So let's call this un plus 1. And that's going to be an array of the same size as un. Un, remember, is an array in space. Contains n points, or however many points in space, okay? Not in time, okay? It's an array of points in space. un plus 1 is the same size because we're just advancing the array at un to n plus 1. So we can do this with NumPy, and we're going to initialize that to 0. np.zeros like un. You could have said, I'm going to create an array of zeros of size n. Okay, but we have that. And or you could say, I want it to be like un, either way. So you could do this or that. Just want to introduce a new syntax for you. Okay, so this creates an array that looks like un. Same shape, really. That's what it is. Or you could have said, np.zeros of size n. You already have n over here, defined over here. Okay? But it's all zeros. Okay. All right, so now I'm going to write this discrete formula over here. I'm going to write it and then explain it, okay? I'm going to say un plus 1. Now, this un plus 1, this formula, does it apply at the boundaries? We are given boundary information, right? Does it apply at the boundaries? It doesn't, because we are given information at the boundaries. So really, this formula only applies at the interior points. What can we use to access a subset of an array or a view of the array? Slicing, exactly. So un plus 1 from on the interior points. So now compute un plus 1 at the interior points only. Yes?
So when you say interior, you mean points that are not at the outer bounds.
Mm-hmm.
That's because you can't do your central.
And not only that, I have information at the boundary already. We can do one-sided at the boundary. So if you hit the boundaries, instead of doing a central scheme, you can do a one-sided second-order scheme. You don't have to reach outside the boundary. But the fact I have information at the boundary, and that information trumps the equation itself. There's no degree of freedom at the boundary. You are controlling that. The process only at boundary plus and boundary minus occurs, right? Okay, it's trying to adjust. You set the boundaries, and that's what sets the unique solution for your PDE. So really, I cannot apply that formula at the boundaries. Okay? But that's a good point you raised. If we're doing central, we're going to get off the grid points. Then you could do one-sided differencing. There's a solution for that. Amir.
I'm just a little confused about the code. You said un is equal to solution into -1.
Mm-hmm.
So you indexed one solution, like one number. How is unp1 the size of un if it's only one?
Because it's no sol -1. Okay, so let's try it out. Okay, let's say I have an array A is equal numpy dot array, and let's do 1, 2, 3, 4. Okay, and then I create sol or Amir sol. Okay, Amir sol dot append A. Okay, now what is inside Amir sol? What do you think is inside Amir sol? If you print it, print Amir sol, it's going to be one array A. Okay, what's inside Amir? So let's now add another one. B is mp.array 7, 3, 34, 4, 5, and 6. Okay, and then say Amir sol.append B. Okay, so now if you print Amir sol, there's two arrays. Okay, what is the most recent one? It's going to be this one. Okay, makes sense. It's an array of arrays, or a container of arrays, right? It's a list, like a list. Really, it's a list. Okay, makes sense? Yeah. So now when I grabbed un sol -1, that is going to give me the array, okay, of un in space. Okay. Now I make a new one of the same size. All right. So now let's compute this formula. We have un plus 1 is equal ui at n. So same thing at all the interior points. So I'm going to say un from 1 to -1. Agreed? So think of this as a for loop. When Python sees this, it says, oh, each point in this array is equal to the corresponding point in that array, 1 to 1. Okay? Agreed? All right. Plus dt times, or mu, times dt over dx squared. Okay, so that's that formula, mu dt over delta x squared. What's nice about Python is very faithful to your formulas. Okay, so is MATLAB, some of these higher level programming languages. All right. Okay, now is the hard part. So if you get over this, then that's a big step in like thinking about Python and CFD. So how are we going to do this piece? This -2 uin, okay, that's fine. That's minus 2.0 times un from 1 to -1. Okay, that's fine. Yes?
Sorry, the dt divided by dx divided by dx.
Yeah.
Is that the same as dx squared?
Mm-hmm. Yeah, because...
I thought it would be dx and then divided dx by dx.
Yeah, divided by dx, divided by dx, it's 1 over dx squared. And that's better this way because I always try to avoid using powers when programming, because powers cost more in the code than actual multiplications. Because powers are evaluated with like some fancy other algorithms. So always if you have integer powers, now some modern codes are smart enough to detect integer powers or integer divisions, but I always opt for that, divide, 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 or multiply. That's why when you see me do dx squared last time, I did dx times dx, not dx to the power 2, okay? All right, so what about these two terms? This ui minus 1 and this ui plus 1. Now, when you think about it in terms of an array, so let's come back here, okay? Let's come back here. Forget about the boundary points, okay? The ui minus 1 points, so if you are here, this is ui minus 1. If you are here, this is ui minus 1. If you are here, this is ui minus 1. You are here, this is ui minus 1. You are here, you are here. So ui minus 1 is really the set of all of these points, right? What is ui plus 1? You're starting at this point. This is ui plus 1 for that point. This is ui plus 1 for this point, ui plus 1 for that point, and so on. So ui plus 1 is really the set of points to the right of point ui. So what if we create views of the array that give us all the points to the left of point I and all the points to the right of point I. Wouldn't that work? Let's try it. Okay? So what is this going to look like? All the points to the left of point I are going to be un. We're going to start from the beginning all the way to -2. That's right. Okay? And then all the points to the right are going to be un from all the way to the end. So, all right. If this is not clear, let's do it on this example array here. So A is 1, 2, 3, 4. Okay? So if I take A from 2 to the end, that is going to give me those last 2 points. And A from the beginning to -2, that's slicing, is going to give me the first 2 points. So then, when I'm going inside the array, inside that formula that I have down there, as it goes through each point in the array, it's mapping point I to point I plus 1 and I minus 1. Think of this here, what Python is doing internally. Python is doing a for loop. It's going through the first point in this array. Okay, first point in this array. First point, what is the first point in this array? It's the point to the left of this point. Okay, and so on and so forth. So when you do it this way, that avoids a big, nasty for loop. And it's actually more efficient because this is compiled code in Python, not interpreted code. So when Python sees this, it runs a very efficient C code that executes this. So it's much faster than doing your own for loop. Okay? I know you're going to have a lot of questions about this, but you'll see that this is going to work. And you'll grow to accept it over time. Yes?
Is it called vectorization?
Yes, it is like vectorization. That's correct. Yes. Now I'm going to set the boundary conditions, set the BCs. un plus 1 at 0 is equal to 0, and un plus 1 at -1 is equal to 0. So that's the last point. Okay? We're done. Solution.append un plus 1. Now I have all of the points done, advanced one time step. Okay? And I'm going to store them in sol. And then I need to advance t. So I'm going to say t is equal to t plus delta t. Okay? You think it's going to work? Why don't you run it? And then try to plot it. I will share with you some slides about kind of where the logic here is for this diffusion term, +2, -2, etc. You get an overflow? Okay. Well, we got Maher helping us. Do I get an overflow? Are we dividing by 0? Can we brighten this a little bit? Yeah, sure. Let's see. Multiply over dx. So what is dx? This one, can you print dx? And add when you're adding. So let me see if mine runs first. What? It shouldn't be. Oh, I get an overflow as well. That's crazy. Okay. Let's see what's going on then. Where did we make a mistake? Okay, do you think we made a mistake somewhere? Runtime overflow encountered in multiply. So mu dt dx times un. So I want to see what this one is doing here. So we have I mu delta t over delta x squared and dt. So let me print dx. X. Okay, so dx is good. And then I'm going to print this guy. Okay, pardon me? Yours what?
Mine's all, I don't have
It worked? Okay. Yeah. So, see? Oh, I see, Maher, you're thinking it diverged, right? Yeah, okay. So did you put it for 10 seconds? Okay, so yeah, let's, yes, now, yep. Okay. So actually now, just bring the time step down a little bit, okay? 0.01, So go 1 e to the minus 3, that's right. So, okay. So now at least we have a solution, but also it was good that we didn't have a solution, okay? Because all the numbers were okay, but there was something going on. We're going to get to that point in a second. It's just we integrated it too far in time. It's through a warning, but we could still have plotted it, okay? But I want you to see a nice solution first. Okay, so you run this, and then you say, okay, what am I going to do? plt.plot. What are you going to plot? All of them. You start with sol1, and then sol2, and then you can't see a darn thing, okay? So go ahead and grab that animation snippet that I sent you over Canvas, please. And I want you to include it here in the code. So I'm grabbing it right here. Okay, and delete, there's like this any.save deleted at the bottom. So grab your animation snippet from Canvas, please, from the announcement. And just paste it here as is. We'll talk about it in a minute. And now this is not going to work because you have to import a couple of things for it. I should have shared the imports with you, but that's okay. So you would need to also import. So now we're almost completing our boilerplate. You need to import matplotlib.animation as animation, and set these parameters for Python. I know it's like, how the heck do you find that out? You just find an expert in Python who tells you about it, and then just move on in life. You find it once, you hook onto it, it does its job, and you move on with life, okay? So try to do this. This will give you really nice animations in your notebooks, okay? So set the type of animation HTML so that it looks nice and not ugly. And just import the animation module from matplotlib. Okay, if you're done with that. Oh, okay. Yeah. I should actually just share it on Canvas. Sorry about that. Should have shared it on Canvas. I'm going to edit the announcement. Apparently, I can do that. Can I do that? I should be able to do that. Announcements. I'm going to reply to my own announcement. Okay. So I added a reply to my announcement. You should be able to see that on Canvas as well. All right. So now you go down here. This will create an animation for you. And you could save it, or you could just view it in the notebook. What this is doing here, it's looping. What I want to do, the nicest animations are those that are done when you create an image of the animation, of the plot, of each plot, and play them in a sequence. Then you can control your frame rate, your delay, etc. In practice, what I do, I actually export all of these solutions as PDFs or SVGs, and I animate those with another tool. But for the intents and purposes, for this course, this is the closest to doing that, okay? Now here, what I'm doing, I don't want to output every frame, because you got like what? It's running over 10 seconds at time step 10 to the minus 3. You have thousands of frames, right? We don't want to animate all of those. So I'm going to skip every maybe 10 frames or 20 frames if I want. So this is looping over the solution. And this is saying every 20th frame, plot it, and then and set the limit. So I'm going to set the limit from -1 to 1, or minus 1.1 to 1.1, because this is a sine function, goes from minus 1 to 1. So I have a nice kind of, if you don't put the limit, it's going to change the y-axis, because I know this is going to decay, and as it decays, it's going to shrink the y-axis. Doesn't look like a nice animation. In fact, it will give you the illusion that nothing is changing, because it fixed the figure width, right? If we fix the figure width, the figure height at 4, right? So you need to fix the limit. Fix the limit to the same initial condition that you started with, all right? And then it creates an animation for you. Then to view the animation, type any over here. And it's going to crash because I didn't run this. All right, so I'm going to run this now. And I'm going to see what's happening here. You can dig more into what these parameters mean. They've worked so well for me over the years. The only thing I would change is the y limit here and that output frequency of frames. Now, that's a lot of frames to plot, frankly, so we'll just give it a second. Animation size, OK. So, yes?
The code that I copied from Kansas is different than what we have on screen.
Is it? What is different about it?
Pretty much.
Everything?
Like inside the PLP plot, there's
Oh, yeah, sure. Yeah, but those are like minor differences, right? So you can do, OK, what did I have minus? Solution. Yeah, OK. Just plots, change it to this one. Change it to this one, please. And then what I had here was KO minus KO, right? And marker size equal 3. Size equal 3. Yeah, I see. It's just some of the settings, right? Because, yeah, for different initial conditions, I'm going to do different things, OK? But that's the extent of it, OK? So let's do maybe at 40, skip, run it again. Did it work for anyone? Do you have any animation working? Still running, yeah?
Mine works.
OK. All right. So this is what I see here. It's a little bit large, so I'm going to make it 100 dpi's, a little bit smaller in resolution. Still look nice. OK. So this is what I see. And if I run it, yay, it's decaying as expected, right? And it's trying to match what the boundary conditions are telling it to gravitate to. Boundary conditions are set at 0. They're consistent with the initial condition, starts from 0. OK. Not working? All right. So we'll be floating around. Working? OK. It's still running. Yep, it's taking a long time. OK? Yeah, because there's so many frames. Yep. Yay, there you go. You got it. OK? So maybe do, 50 frames. OK. Oh. OK, I know what's going on. So scroll up a little bit here. Yeah, clean up this solution here. So, OK. Almost. Animation is not defined, so you got to run this here. Okay, let's run it again. OK.
We need to run
still?
the time loop.
Oh.
We did the restart.
Oh, you did a full restart?
Yeah.
OK, so let's just run all cells. OK. You guys got it here? No? What's happening? Nothing? But do you have a solution? This is still running, so go up. Scroll up. This is, yeah. So now, OK, now it's running. Now this is running. OK. Yeah, it's going to take a long time. Either use a smaller number of times of smaller end time or skip more frames for it to go. You got it?
mine is doing an error, but I'm using Spider, so
OK. OK. Yeah, this won't work in, you have to save the animation if you want to do it in Spider. Did it work?
Still running.
Okay, so you're doing 50 frames. So maybe do a smaller end time, Brandon. Yeah, now obviously it's going to depend on how fast your computer is, okay? So maybe this was an overkill. But I wanted it to be exciting, right, where everyone got it. But most of you got it. You got it? Okay, excellent. All right. So if you want it to run a little faster, I know you'll spend more time generating visualization in CFD. So imagine how annoying this was in 1D. So imagine when we go to 2D and trying to animate this in 2D. And you'll spend more time animating your data and visualizing it than actually computing it, right? Okay, so you can shrink your time a little bit, maybe go to 3 seconds, for example, and that will give you, that will be a little faster for you. Or skip more frames. Okay. Maybe do a smaller end time.
It's not even running.
It's not even running. It's still running, the time loop? Crashing? Is it crashing?
Crashing. Not running.
What do you mean it's not running?
It has the waiting. Simple.
So it is running. It's still in the loop, right?
Yeah, but it's using 0.01.
Yeah, it's probably because of the overflow. Yeah, so and that's gonna diverge actually. All right. So just use this number, maybe choose a smaller end time. Okay, so go maybe to even 1 second, okay? Go to 1 second. And you could at least just see it decay a little bit, okay? All right, now what happens, let me try a different, let's stick with this time, okay? And we said we were gonna try some different frequencies, right? So we started with this, this is 2 pi, right? So let's go to maybe 4 pi, see what happens. 4 pi, okay, great. Let's run it, simulate. Okay, let's see what happens with 4 pi. Oh, do you see something? What? It's decaying faster. Okay, should we form a hypothesis? Maybe we collect one more data point and come up with a hypothesis. Okay, so let's go to 10 pi. Okay, it's a high frequency signal, a lot of noise, maybe. Let's run it. Okay. Okay. You stand right. Okay. So our hypothesis now is that high frequency signals diffuse faster than lower frequency ones. Okay, we will demonstrate that later. Okay. But let me show you this cool little trick here. I'm going to take 2 signals. One that is a very low frequency, so mp.sine of 2 times pi times x. And I'm going to superimpose on it a high frequency signal like this 10 pi or 30 pi. And I'm going to add more points. This looks like this. Okay? If our hypothesis is correct, and let me train your vision here, there are 2 scales, 2 length scales here. The long wave, which is this wave, right? Or the low frequency signal, but there's also the high frequency signal on top of that. If our hypothesis is correct, what will happen, those high oscillations or the noise is going to decay faster than that big frequency. So within a few time steps, we're going to see those collapse into a main frequency curve. Let me make this even a little bit better by scaling that 30 pi frequency by 0.1. Okay, so it looks like noise on that big signal. Okay? Maybe 0.2. Okay, let's run it and see what happens. Okay, look at that. Almost instantly. Let me add more frames to it, maybe do 10 frames. Okay, I'm going to step like one step with this. Look at that. Within a single, like if you, this is 10 times steps, right? We smoothed out the high frequency signal very quickly. But then the low frequency one is still there, and it's going to take its time to decay. Okay? So Amir asked me a question last time that the decay is logarithmic or something. It is not. It actually depends on frequency. The decay of a signal in a diffusion process is a function of the frequency. We will show later that that decay is e to the minus mu times the frequency squared times. Okay, but at least observationally, this is nice to know, and that's each other. Okay, so let's go back to our initial one, which was this 2 pi. I still have some time. Now I want to come back here, go to 101 points. I want to look at that overflow condition. So I'm going to change my time step to 10 to the minus 2. Okay, obviously, and I think if we go smaller, we know that it's probably going to be OK, because that time step 10 to the minus 3 worked. A smaller time step is definitely going to work. All right, so let's go a higher time step size, and let's see what happens. Okay, I'm going to run it. Okay, no errors, right? But let's see the solution. Let's see the solution. What happens? Oh, what the heck? Let's go back, let's go back, let's go back, let's go back. Everything was going well. Okay, so 1, 2, go, go. Boom. Okay, so maybe I should go 1 frame at a time. So I'm going to save each frame. And I want to see what happened, like at that time step where the solution went crazy. I was like, I don't know what's going on, right? Okay, so let's go step, 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 step. It's decaying correctly. It is doing OK. It's doing OK. Oh, whoa, whoa, whoa. Look at that. What the heck is going on here? Poop, poop, poop. Gone, right? It's gone. We say the solution has become unstable. Cuckoo, you know, went unstable, unbounded. Okay? Let's go back to the slides. We're going to need some theory to understand that. Obviously, any time step that's higher than this is not going to make things better. Okay? So there's like a time step size where things are OK, and another time step where things are not OK. Okay. So you'll find that for some of the time step sizes, the solution is oscillatory and eventually unstable. You start forming these high frequency oscillations at every grid point, right? Up and down. We will learn more about stability later. We'll do more formal stability analysis. But today, I want to give you wet your beak about how intuitively you can think about stability. And an intuitive approach, this is one of the nicest ways that actually I worked through this like between last night and today. And I think it's one of the greatest explanations to think about stability. An intuitive approach is to consider what happens in a single time step to a pulse. So we're going to take the entire grid in 1D. We're going to put zeros everywhere, the initial condition. And at one grid point, we're going to put the value 1. Okay, so this looks like it. Just one value everywhere else is 0. Okay? So consider this situation. Your initial condition, time level n, or really at any time level n, that's the initial condition. Everywhere is 0, except at some point, the value of u is 1. Okay, and I'm going to discretely try to move this a single time step. See what happens. This was our formula. I would like to rearrange this formula as such. So I'm going to, there's uin over here times this, and uin here. So I'm going to combine them together. And what you get is the following. Some coefficient beta times ui minus 1 at n. Beta is mu delta t over delta x squared. right? So that's beta ui minus 1 at n. And then 1 un minus 2 beta un, right? This guy. And then the last guy, beta ui plus 1. What is beta? Beta is mu delta t over delta x squared, and that's called the Fourier number. Okay? The Fourier number is a measure of diffusion over a given time scale. So what this is telling us here, the Fourier number is measuring within a single time step delta t, given some diffusivity mu, over a length scale delta x, okay? It's measuring the rate of diffusion over that length scale. Now, it's scaled correctly as delta x squared because diffusion needs, this is meter squared per second, this is second, so you get meter squared over here and you get meter squared over here, so it becomes a dimensionless number. But it's a measure of how fast diffusion is going within a single time step over the length scale of diffusion, which is delta x in this problem. That's really your length scale. You define that length scale of diffusion. Okay. Now, for the diffusion equation, what do we expect to happen for this pulse? You have 0 everywhere and 1. We expect 1 to drop, and the zeros next to it to go up a little bit. Okay? And then for that process to continue. We should not expect negative values. Agreed? Because the boundary conditions are anchored at 0. It's never going to go negative. Okay? And we should not expect, and the same applies if the signal is negative. If the signal is actually negative, it should not become more negative, right? So it should decay. It's going to become more positive in that case, okay? So we should expect that 1 to drop a little bit and the zeros to increase just a little bit, and that the signal cannot be negative. So we cannot have a negative value at 1, okay? So let's take a single time step here. So again, this is our formula, okay? So you can apply it. You can take this point and say, okay, this is beta ui. Okay, forget this point. This is the boundary. Let's take this point. This is beta ui minus 1. Ui minus 1 is 0, so there's 0. And then 1 minus 2 beta ui n, it's 0. And then plus beta ui plus 1 n, it's 0. So you get 0 here. You still get 0. And then you continue over each point. You get to this point. Okay, this is beta ui minus 1. Ui minus 1 is 0, so this first term is 0. 1 minus 2 beta ui n, ui is 0, plus beta ui plus 1 at n. What is ui plus 1 at n? It's 1 times beta, so you're going to get beta over here. Okay, so you continue this process, and this is what you get. Okay, agreed. Something happened to 1. It changed. It became 1 minus 2 beta. Okay, and the 2 points neighboring it, they inherited some value from 1. Okay, they got a beta and a beta. Okay, and if you add them to each other, they still result in 1, right? Because we shared that 1 value with the 2 neighboring points, right? So this one dropped by 2 beta, and this one inherited a beta, this one inherited a beta. We're distributing information equally, okay? All right, so now we can make a statement about this, okay? We can make a statement about this. What is the condition on beta for this to be a diffusion process? Obviously, these 2 points can never go above 1, okay? So we know that beta is less than 1 from these 2 points. Good, all right, we have a condition on beta. Now, beta is important because it has delta t and delta x, so it's going to help us choose delta t. If we fix delta x, we have a condition on beta, we can then choose what delta t is. But what about this point over here? We said that, okay, beta is positive, so you know we have at least that fixed, and beta is less than 1 from these 2 points. But from this formula here, we know that we cannot be negative. So if beta is anything greater than 1 over 2, so put beta equal 1 over here, you're going to get 1 minus 2. The signal is going to become negative. Agreed? Only for beta less than 1 over 2. So if beta is equal to 1 over 2, you get 0 over here. Okay? That's at least the condition. We're not negative. If beta is less than 1 over 2, so if it's 1 over 4, then you get a half over here. That's great. You start splitting the signal equally, right? So that gives us the condition, a very, very simple analysis like this. In fact, that's the condition from formal stability analysis on diffusion, that this beta, or the Fourier number, for 1 dimension, this mu delta t over delta x squared for diffusion needs to be less than a half. Very simply, just doing that. No fancy math, no complicated stuff, just an intuitive thinking of a simple pulse. You can apply this for advection, advection diffusion, even for implicit methods. We'll see that later, okay? So when you have this condition, then you can say, okay, if I'm given delta x, I chose it, and I'm choosing mu, then I can choose delta t to guarantee this condition, okay? So let's go back to the code, and if my analysis is correct, I'm going to reproduce this case. I'm going to initialize with zeros everywhere and 1 in the middle. I'm going to take a single time step with the wrong beta, wrong Fourier number. I'm going to show you that it's going to become negative, okay, because of this. All right, so let's go and do this, and then we'll be done, okay? All right, so let's testing stability. Actually, we can just do it here. All right, test stability with the intuitive method, with the intuitive pulse approach. Okay. So I'm going to say U0 is zeros everywhere, mp.zeros of size n. And in the middle, I'm going to put the value 1. So where is the middle? I'm going to take, it's n over 2. So this 2 forward slashes gives you an integer. So it's going to round it to an integer. Okay? So there's no exact middle over here, right? So it's just going to find the closest point to that. I'm going to make that 1. Okay? And if I plot this, U0, sorry. If I plot this, I get this. Zeros everywhere and 1. That's why I don't like connecting them with lines, so I'm just going to make them like this. So you get 1 over here. Maybe we choose a smaller number of points to see this better. So you get zeros everywhere and 1 right in the middle, and then zeros everywhere. Okay? All right. So now let's cast everything in terms of the Fourier number. All right, so I'm going to define my Fourier number. So Fourier number is equal mu times dt over dx squared, right? So therefore, a correct delta t for stability, Fourier number needs to be less than 0.5, okay? So you could choose delta t is equal to your chosen Fourier number times delta x squared over mu. And then you choose the Fourier number here. If we choose 0.5, we are right at the stability limit. If we choose anything other than 0.5, or greater than 0.5, we're going to mess things up. Okay, so let's choose a Fourier number of 1. Okay, so we chose the Fourier number. We chose this mu delta t over delta x squared, and then from that we deduce delta t. So remember, in my slides here, I said Fourier needs to be less than half. Here I chose it greater than half on purpose, because I want to show you that it's going to go negative in a single time step. All right? And then my t end is going to be, I'm just going to do like 2 time steps, 2 times dt. All right? So we chose dt, print dt, we can print it, and we chose t end to be that. All right. And then we run it. Oh, what is mu? Oh, my bad, mu. Okay, so my time step here is 0.25. We know that this is going to blow up. Okay, so let's see. If we plot now our solution, plt.plot, my initial condition is going to be u0, right? And I'm going to do, going to double check that. That's my initial condition. Now, the first solution is sol 1. That's after a single time step. If my analysis is correct on the slides, we're going to see a negative value in the middle. Indeed. Look at that. You see a negative value in the middle. Okay, so we started at 1. Everywhere is 0. Wrong time step size, you create a negative value. Negative value for diffusion is weird, is bad, is wrong, because it's really equivalent to negative diffusion, which is moving against the gradient, right? So that's unphysical. Okay, so it's like you put high concentration of ink, local, and everything comes to the high concentration, right? It's like, it's weird universe, okay? Just a single time step. Now, if we choose the right Fourier number, So let's go to 0.5 right at the boundary. Usually, you're OK. Maybe we put 49, 0.49. OK, you do a single time step. It dropped in the middle, but it didn't go negative. It didn't go negative. That's fine. That's OK, because it is going to stabilize eventually. OK? You go 0.25. That's even better. OK, it dropped just a little bit. Well, it dropped to 0.5, actually, right over here, 0.5. OK? That's cool, isn't it? We will later see when we use another kind of analysis called modified equation analysis that this discrete equation actually does not solve the diffusion equation. Remember, there was truncation error involved when we approximated the derivatives. It turns out that this discrete equation solves the diffusion equation plus something else. And that something else is going to depend on delta t and delta x and mu. And you will see that there's a diffusion term which could become negative if you choose the wrong Fourier number. So you're going to have a diffusion term multiplied by Fourier number minus 1/2. And if the Fourier number is less than a half, you get negative diffusion. Okay, and that's going to crash everything. Okay, a lot has been done today, but we also learned a lot, right? Yes?
So it'd be probably a good idea to have this Fourier check in pretty much everything that you run.
Absolutely. Yeah, so those are stability constraints that we put on all our codes. But in reality, this only works for the linear equation. When we add nonlinearity, it's hard to do nonlinear stability analysis. And so we take the linear analysis and we take some safety factor with it. So we put our Fourier numbers. We're going to have another condition on advection. And when we combine the two, we're going to have a combination of those two conditions, because one of them is going to control the others. Another intuitive way to think about this is that it's not as clear as the advection case, but I'll go ahead and try to do it. If you choose a Fourier number greater than half, you are diffusing information at a scale longer than the length scale of diffusion. So you're trying to diffuse information faster than diffusion can actually do. Why? Because you have a choice as a property of the problem. Okay, and over my length scale, I can diffuse. It's this combination. This is the fastest I can diffuse. When you choose delta t to violate that, you're forcing diffusion to propagate faster than physical diffusion can actually propagate over the squared. This analogy will become easier when we do the advection problem. Or if you want, you could say, OK, if you take, so this has dimensions of meter squared, and this is meter squared. But if you take delta x over here, you put mu delta t over delta x, and you put delta x at the bottom. This becomes length and length, OK? Then at the top, what you have a distance of diffusion, distance, not in area, just a true distance. You're saying you've chosen delta t to diffuse over a distance larger than the actual distance that physical diffusion can diffuse at. And that's why it breaks. You cannot move information. It's like you're bypassing what physics can do in reality. Given a property mu and a delta x spacing, you have anchored the physics of diffusion. I cannot diffuse faster than this. But when you choose delta t to violate this, you're forcing diffusion to go faster. You're trying to skip points, essentially. Diffusion is saying, OK, I can only diffuse in a single time step. I should be able to diffuse from this grid point to this grid point. What you're saying, no, I want to diffuse to that grid point. Well, you can. What happened in the middle? That's why it goes negative, right? OK? Hopefully this was helpful. And for those who are doing the PDEs, welcome to PDE world. It's not that bad, right? It's pretty nice to see all of these. Go and play with the code at home over the weekend. Explore different things. We will add advection, and we'll do advection diffusion next week. OK? Thank you so much. Have a great weekend.